I'll get started. So my name is Simon Riggs. I'm from Second Quadrant, and I'm going to be talking to you today about replication refresh. For people that have heard me talk before, I normally give very technical presentations, quite often about development work and futures and such like this. What I'd like to just point out to you today is that I've been asked to give a talk specifically for novices on an area of technology that we already have. So this is a very different type of presentation. So I hope some of those people that were expecting the really advanced stuff don't give me too much of a hard time while I cover the basics. But if there are lots of novices in the room, please feel free to ask the basic questions, and we'll see what we can do. So what I'm going to talk about is a little bit about plumbing, something about fluid dynamics, something about burst pipes, and maybe about some new features stuff kind of towards the end. So some really basic things. What I would like to do is explain things in a behavioral way. So I'm not going to be talking about parameter settings, and I'm not going to be showing you loads of code about how to set things up. I just want to talk about the way things work, why they work that way, and help you to understand things at a really basic level. So that's kind of my first diagram, and you can see like the type of level that I'm talking about here. So basically, replication, why do we do it? Well, the name replication comes because we're taking a copy of some data on one server and we're transferring that to a second place, a second server. Now with replication, the idea is that that's going to be happening continuously, and it's the purpose of doing it is quite diverse. It might be for high availability. It might be to allow you to load balance your application, or you might be setting up some kind of a test server. There's lots of different reasons. Okay, now these days people talk about replication as if it was so blindingly obvious that you needed it that everybody just says, right, I'll have it. The reason for this talk is to remind you that replication isn't easy. We make it as easy as possible, but it isn't necessarily easy, and you may not want it. You may not want it in all of its forms. Okay? But if you do use it, you've got to step up to the plate, understand it, and make sure you're running it properly. Unfortunately, it's not something that you can just install and forget. Okay? So let's start at the beginning. How does replication work? Well, we use the native Postgres protocol to connect multiple servers together. This is a very important point because it means that the replication connections have identical security characteristics to normal client connections. That means we can punch through firewalls. We've got all of the benefits that we get from security, but most importantly, we're not creating some kind of security hole just because we're using replication. The model that we use is one where the receiver connects to the source of that data. Now that might appear to be the wrong way around. The data flows from the sender to the receiver, but it's actually the receiver that connects to the source of that data. So the connection is apparently backwards to the flow of data. So the reason that we do that is because the standby knows when it's appropriate to connect. If we do things the other way round, all we get is lots of connection errors, standby not ready yet, that kind of thing. So it makes a lot of sense to connect from the receiver to the sender. Now, that means that we need to put all the parameters for connection on the standby side. Okay? Now that doesn't mean there's no parameters on the sending side, but a lot of the connection stuff is actually on the receiving side. Now the current way that we do things presumes an always-on connection. We haven't yet got to the stage where we're tolerant of certain outages, or we're able to cope easily with servers being only available for, say, a few hours per day. So it's not yet fully set up for a fully mobile world, where maybe your iPhone is only switched on for 12 hours a day. One thing that's quite interesting about the way that we implement things is that the replication code that lives on the receiver, on the standby side, is actually a Postgres client. And because that doesn't compile directly into the server, we've actually had to implement that as a plugin. So while you may think it's fully integrated, the current physical replication is actually implemented as a plugin. Now, to my knowledge, nobody's actually taken advantage of that and written multiple kinds of plugin, but it is actually possible in the future that we could have multiple types of replication plugins. I mention that now because some of the things that we're working on in the future are actually, they manifest themselves as plugins, and that might look like it's some kind of a different architecture, but actually it's the same thing. We have gone to the trouble of layering additional security on top of the basic libpq security. So there's a special rule that you have to set up in the host-based authentication file specifically to allow replication connections in from a certain direction. There's also an explicit user capability that you need to set up for replication. So there's two additional things that you need to do to make replication work. Now, that is because replication is so powerful that it really is worth the extra protection that you're going to be giving to it. Okay? Don't imagine for an instant that if somebody's going to hack your server, they're going to ignore your replication. Actually, if they can, it's going to be their primary route in, because that source of data is so valuable, it's basically got absolutely everything about the server available via that replication route. So it's just golden, okay? So protect it very carefully. Hands up who's actually protected their replication carefully so far. Okay, go home and protect it. The next thing that we've done is we've designed the replication to allow you to have multiple receivers at multiple locations. Now obviously it wouldn't be very highly available if we forced you to have only one receiver at one location. So it's very important for data protection that we're actually able to send copies of that data all over the world in various mechanisms via various transport routes. Now the purpose of this, just to re-emphasize, is that allows you to consider the role of the standby servers that you have in your configuration. So rather than thinking of your system as a cluster of similar servers, you can actually think of it as a set of servers that are working together but with slightly different purposes. So for example, you might have a high availability server that is designed to be the target for failover. You might also have a disaster recovery server that's on a separate continent. You might have additional servers for load balancing of various kinds. Load balancing doesn't just happen in one flavor. You might have multiple different kinds of load balance servers depending on the needs of your application. So instead of a cluster of similar servers, you might actually have dozens of servers all working together to solve the total problem, but yet very differently configured. Okay? So it's important to understand that the servers don't know what they're for. Okay? if you want that server to be a high availability server, you have to indicate that via the preferences on the configuration settings. The server doesn't know, okay? So you can't thwack it around the head and say, damn it, I wanted you to be a high availability server. It doesn't work, okay? So you have to define what those servers are for and set things up appropriately. The whole system is designed to be very efficient and concurrent. On the master node, the dark blue node, we actually have separate processes responsible for sending data to each of the receiver nodes. So if there's a blockage, a network problem on any of the standby nodes, that's not going to affect what happens on the master. There's no effect on the latency when we have a problem on any of the standby nodes. On the receiving side, we have multiple processes dedicated to making the replication work. First of all, we have a dedicated receiver process that handles the communication with the sending node, and we also have a dedicated apply process that will be applying the changes that have arrived from the sending node. Now, all of these processes are all acting completely independently of one another, and so across the whole server farm, you'll see that we're actually getting a very high degree of concurrency there, and I hope that that's been done in a very efficient way. In terms of power usage, we've designed the interactions between all of these processes to be ones where they actually sleep on a latch. Now what that means is that if there are no changes to be sent at any one time, then the processes very quickly go to sleep. So they'll use no power at all, but as soon as something happens, they will suddenly leap back into action at full speed to handle the communication, handle the apply, and then go back to sleep again. Okay? So it's both efficient in terms of performance, but efficient in terms of power utilization across the combined cluster. The next thing that we've designed into the replication is what we call cascading replication. And the idea here is that we're able to chain the servers together so that we don't just have master to slave, we're actually able to have master to slave to slave to slave to slave. Now that allows us to come up with very complex configurations for a distributed cluster, and it also allows us to minimize bandwidth costs, because bandwidth costs are probably one of the most significant costs in this type of environment. It also means that we need to understand the configuration of the servers that we're setting up in terms of three potential roles. A master will have a certain number of considerations associated with it, but so will sending servers. So a master is obviously a sender, but the intermediate cascading servers are also sending data onto other nodes. But the mid servers are also receivers, and just as we had before, multiple processes working concurrently, the mid-tier cascading servers are literally sending and receiving independently on separate processes at the same time. So again, full efficiency, full concurrency. So the receiver nodes, which are normally called standby processes, we do have read-only access to them by something called the hot standby feature. And I'll explain that a little bit more as we continue. But the basic idea there is that what we're doing is we're actually recreating the concurrent transaction environment on the standby. What I mean by that is all of the transactions that are created and committed on the master have information analogs in the standby. So if you've got a long-running transaction on the master, we actually make it look like there's a long-running transaction on the standby. So all of the ways that MVCC works on the master also works on the standby. So information appears in the database in the same transaction log sequence that it would be appearing on the master. Okay, so that's actually a very important point in the sense that the standbys do actually work almost identically to the master, but we're actually doing that by spoofing. Those transactions are not executing again on the standby. We're just replaying the changes on the standby. So if I didn't say it before, one of the reasons for giving this talk was because I've seen actually quite a lot of incorrect comments from people about how things work or the implications of things specifically around different behaviors that are displayed by replication. So what I'm trying to do via this talk is to get some correct information out there. Pretty much all of the actual sort of technical configuration setting stuff I've seen, that's correct, and you can look it up in the manual. But what we don't necessarily have is a good description of the behaviors. And I'm not precious about questions as well. If you want to interrupt me with a question as we're going, please just shout it out. No, apart from you, Robert. So in terms of... Really, no. Do you actually have a question? You just wind me up.
Okay, look. You're going to have a question.
Oh, I thought it was him. I thought it was him. Sorry.
Do I look like him?
No, I just heard the voice. I went, oh, okay, here we go. Heckling starts.
He's like, Robert. Okay, it is a question.
Okay.
Right? Okay. I worked on a configuration once. We had a client.
Yeah.
The client was a very fast-acting broker. It would go into a master-slave configuration. Now, the rate of propagation from the master to the slave wasn't high speed, it was asynchronous.
Yep.
The client would go in and it would say, oh, it was round robin. It would hit whatever it hit to look for a transaction that it put into the master.
Yep.
Is the transaction ID here going to be the same as in the master?
Yes, absolutely. I mean, that's the way that we track things, is via the exactly the same transaction ID. What used to happen from 8.2 and earlier was that read-only transactions were allocated a transaction ID as well. What we do now is if a transaction is read-only, we don't actually give it a full transaction ID. So the only things that are given full transaction IDs are write transactions, and we use exactly that same write transaction ID to recreate the changes on the standby. So it is actually completely identical. So if you said, is transaction ID 37 running on the master, you go to the standby and you get exactly the same answer from that query.
All right, that's the good validation test. The client,
Yeah.
so the broker goes in, validates that is exactly the ID, and then it's safe to pull that information out.
Yep.
Okay,
Cool.
and I'm not him.
Oh my God. Oh, I'm going to have hell to pay now.
I have a question.
Oh my God. Okay, so can I press on? Do you actually have a question?
I was just going to ask which one's Robert.
Okay, go on.
Actually, we're both.
I actually knew.
Go ahead.
Can I continue? I mean, you can have other questions on other slides, it's okay. So, what I wanted to talk about was the visibility of changes, because what happens is that the changes are made on the master, and then those changes are shipped to the standby where they are applied. So a transaction can have made, say, 100 changes, and all of those 100 changes may have been applied to the standby, but it's not until the commit for that transaction is applied on the master that we apply the commit on the standby, and then suddenly all of those changes are visible. Okay, what that means is that if you have a transaction that runs for a whole hour on the master, those changes will be applied immediately on the standby. So when that commits on the master, it doesn't take an hour for the changes to be applied on the standby. It takes maybe 50 milliseconds. It's all that we need is the commit record to be sent across and applied. Okay, so the changes are almost immediately visible. But it's interesting to note that the changes appear on the standby after they have appeared on the master. So it's possible that you could ask a question on the master and get one answer, ask the same question at exactly the same time, and get the older version of that question. Okay? Now that's important to understand. It's in practice almost impossible to recreate because of if you send the same question to two different places, of course that question arrives at different times. So you can't guarantee that you've actually asked that question. So we get into sort of some kind of weird physics problems there. But it's important to understand that it happens after. Now that's what we mean by eventual consistency. Okay? That means there's a delay between the commit on the master and the appearance of that commit on the standby nodes. Okay? But it will eventually appear. Okay? There's no doubt that if it committed on the master, it might not appear on the standby. It will appear eventually. Now, if you've got multiple standbys, those changes can appear on those standbys at different times. Now, there's no guarantee that they will appear on those standbys in a consistent order. So it might be that it appears on node B most of the time first, but it might also occur that it appears on node C sometimes as well. Okay, so that's important to understand. So streaming replication gives a very low latency most of the time. The default is asynchronous replication. Now what that means is that bursts of speed on the master will build up a set of changes, and then those changes will drain through to the standbys where they will be applied. So asynchronous replication means that when you get a burst of speed on the master will not be slowed down just because there's lots of replication happening. Okay? But what will happen is the replication delay between the master and the standby can increase and then come back down again. Okay? So with the asynchronous setup, you've got to be very careful to monitor the replication delay between the master and all of the different standbys. Now, one thing that you need to be aware with the latency is that all actions that generate data changes will affect the latency. So, for example, when you're using physical replication, running a vacuum full on the master will generate a whole slew of data changes, and that will affect the replication delay. So if you want to, you can just have a look at that, run a vacuum full or run a big vacuum on one of the larger tables, and you'll see the replication delay spike. Now it's important to understand that the replication delay is effectively the amount of data loss that you will experience in case of problems. So the fact that the replication delay is 0 when there's no changes occurring doesn't mean you're perfectly safe, because the thing is, when you start to make changes, the replication delay will spike. Okay? So you've got to keep very close watch on the replication delay. And that's why I said earlier, if you want to have data protection via replication, you have to manage it. It is not fire and forget. Okay? It doesn't work that way. Now, one thing that we've added to Postgres is, I don't know why I'm speaking into this, because, sorry, question? Yeah. That's a good point, yeah. Well, I mean, this is essentially a business judgment call. I mean, if you're running this set of jobs at a time where it's not affecting anybody else, and if you lose that data from that set of jobs, you can always rerun it. You're not experiencing any increased risk just because the replication delay is increased. Whereas if that was a different, more important set of data, then it would represent increased business risk. But that's a judgment call based upon your knowledge of your data. Yeah. So there's not necessarily a direct connection between the technical numbers and the business impact of those numbers. Yeah.
Is it possible to create a latent replication?
If you want to. There was a patch, I don't know if Robert's here, Robert put in a patch to put in a sort of false delay as a way of structuring that. Now that was originally rejected by myself because it didn't work in all cases, but we kind of recently rediscussed that concept, and I think it's probably going to go in because it's sufficiently useful that although there's a slight flaw in the way it works, it's still useful. So that would go in, and then that would allow us to effectively put in as you say, a false delay on things. Now that sounds great, but obviously remember, if you've got say 1 day's delay on applying changes, that's an awful lot of data you've got sitting there. So you need some big disks to manage all of that data. Yeah. Any other questions, Robert? Good. Okay, so synchronous replication. So synchronous replication is very important because it gives us the possibility of getting 0 data loss. But we need to understand exactly how that works and what the guarantees actually mean, because there is substantial misunderstanding about how this works. So the guarantee that we give is that committed data is safe on at least one other node before we reply back to the user. So if you've got 7 standbys, when you set up sync rep, we're nominating one of them to be what we call the sync standby. Now there's only ever one sync standby at any one time. Now what you can do is you can define a sequence of nodes so that if that sync standby goes down, it will immediately and very quickly switch to the backup sync standby. And if that goes down, it can switch to another one, to another one. So you can have a whole list of standbys that indicate what order you would like to manage them in. But there is only one sync standby at a time. So there's no kind of quorum vote on how it works. Now, because of the way synchronous works, we're actually waiting, the master is waiting for a response from the sync standby before it passes the commit back to the user. Now that means that the response time on the master is reduced, possibly considerably reduced, by the latency to the sync standby. Now that is not the same thing as busy work. What we're talking about is a delay. That session just goes quiet while you send the message to the standby and then get a reply. So it's possible that while you're running with synchronous replication, if you doubled the number of connected sessions, you might actually get the same throughput on the master that you were getting previously with asynchronous replication, but the response time on any one session will be reduced because of the delay for synchronization. Okay? So just to describe the guarantee again, if we get a reply from synchronous replication that a commit is safe, that means that that data for that commit is safe on at least one other node. If we don't get a reply, the data may still be safe, okay? Because if we crash while we're waiting for that message to go all the way to the sync standby and back, it's possible that we crashed in a way where the data itself is safe, it's just the message that was not received, okay? So actually, when we think that we crash, we may actually still have safe data. It's just that we don't know, okay? So there are times when you may wish to check after it comes back up what happened. Now, there's another aspect to sync rep that is widely misunderstood, and that is if there is no sync standby at all, we wait forever. Now, that is not a flaw in the design. I thought it was a flaw in the design, but I was wrong, okay? Doing this makes it correct, okay? Now, there's an important thing to understand here, which is if you've only got 2 nodes and the standby goes down, it will wait forever, okay? So the moral of the story is not don't use sync rep because it's crap. The moral is use more than 2 nodes, okay? So sync replication is kind of pointless unless you've got at least 3 nodes, okay? Is that clear? You've got to have at least 2 standbys.
So maybe we can use all the 2 nodes and monitor if the blade is running, and if it crashes, we can turn off the secret.
Well, that discussion was had on list for about 4 months, and I was championing that viewpoint, and I say I was wrong. If you turn off synchronous replication when the thing fails, then it's like it never was turned on in the first place. So if you care about synchronous replication and you want 0 data loss, you need to have multiple standbys configured in such a way that you do actually get a reply.
Yeah, I understand. So this is kind of introducing the single point of failure
Yep.
for short time basis. Well, if it's okay with configuration, keep working.
Yeah, I mean, obviously you can physically turn it off whenever you choose. What I'm saying is if you turn it off in that way at the point of failure, you may as well have never turned it on in the first place. Yeah. So just to make that extremely clear again, if you have 2 nodes in your setup and you do not have any intention of having more than 2 nodes, don't ever turn on sync rep, okay?
Maybe if I could make a suggestion then, if the system becomes aware of itself, there should be some sort of logging or messaging that indicates if you're running in sync, say you've only got 2, be advised, log it, message it somewhere.
Well, it's kind of difficult to count the number of standbys in a meaningful way because you might be transitioning between things and you don't necessarily want it to.
The objective is to create an environment that allows people to become aware of what they're doing. We need to have some sort of messaging.
Yeah, but the same thing that you can put it in the config with a big, huge disclaimer, don't turn this on.
Whatever you do.
I think we do that with external monitoring, not within the database, because the messages, I mean, if you've got, there's various ways of setting up monitoring that will actually count the servers that you want to have turned on, and then if they're not there, it will message you. Yeah.
I can see people
They will
doing
do a
it.
lot
I
of
can see it. 2 nodes, synchronous replication. They'll do it and they won't.
Well, yeah, I mean, that's why I'm here
yeah, like
telling you not to. So,
you can't patch the entire like, universe of possible configurations. So.
It's like a gun. You have a safety. It's nice if you tell people there's a safety.
yeah, well, I am. This is me telling you. So,
Interesting sounds expensive. Do I have to use it all the time, or just can I
well, that's a nice question. Thank you for setting me up for my next slide after this one. All right. So, but thank you for the question. So, just before we get to that particular point, synchronous visibility. When you've got synchronous replication enabled, it's important to understand that it's the other way around from asynchronous visibility, in that changes appear on the standby before they appear on the master, okay? Because of the way that we do the correctness of synchronous replication. So we commit on the master, but we don't remove the entry from the proc array. Now what that means is it's committed, but it's shown as still running on the master, but we pass the change across to the standby, apply that, and then reply back to the master. So the visibility is slightly different in that case. And
That
what?
only applies to the synchronous replicate, right?
Yeah.
It will only appear on synchronous replicate before
Yes.
the master, and all the other replicas will appear after.
Yes. But the point there is that synchronous replication does not give a uniform viewpoint of the database. Okay, so synchronous replication does not mean synchronous visibility. Okay, that's important to understand. So, in answer to Peter's question, which is, if synchronous replication is expensive, how do we modify things in such a way to not be crippled by it? Well, one of the ways that Oracle works is they have this mode called maximum durability mode, and it's basically an on-off setting at the whole database level. So you either want everything protected or you want nothing protected. Okay. Now that sounds great, but in practice, in the real world, we have certain types of data, such as the lady at the back indicated, that is not critical to the business function, and we have certain data that is critical to the business function. So what we have with Postgres, and this is the only database that has this, is a user selectable setting that allows us to control the durability of a particular transaction. Now the way that this is done is such that the durability of individual transactions can differ even on a concurrent workload. So that means that we can protect certain transactions with the safety of synchronous replication, while at the same time allowing some other types of data to pass through more quickly, but with less durability. And we actually have 4 levels of durability that we can set on that. And most importantly, it's set at the transaction level. Okay, with MySQL, with MyISAM, it's set at the table level, which means that if you're using MySQL, if you're using MyISAM for one table and you're using InnoDB for the other, you get a kind of weird, you can get half a transaction committed if you crash, which is not a good situation to have. And plus, you cannot control things at any lower level than the transaction level. So this is a very important capability, in that we have the full protection of synchronous replication, and yet at the same time the ability to mix our levels of durability in order to gain better performance. So I said I'd talk a little bit about fluid dynamics. Well, what am I talking about there? Everything I've told you up to this point does not presume what type of data we're replicating. Okay? Those of you that already know about Postgres replication will know that we are replicating the physical transaction log, what we call the write-ahead log. So the data that's getting transferred is that physical low-level transaction log data. Now, everything I've told you up to this point would still be true if we replicated other types of data. Okay? And so to understand what the future is going to be like is that we are going to be able to replicate multiple types of data, not just physical transaction log data, and all of this will still work the same way. Okay? So whereas I told you that I wasn't going to tell you anything about futures, okay, what I want you to understand is that the past and the future are going to be the same. All of the same thoughts that you've had about what the way replication works can still work that way in the future when we develop new kinds of replication. But at the moment, we're restricted to just the one kind of replication. So we're replicating physical transaction log data. What that means is when we apply the changes to when we apply the changes on the standby nodes, we are not re-executing any searches, we're not re-executing anything, we're just literally directly applying the data block changes. Now what does that give us? Basically that imposes certain restrictions. It means that we have a single master. It also means that we have read-only standbys because we're not able to make writes of any kind to the downstream nodes. We have the benefit that we're able to handle DDL automatically, which gives us considerably reduced management costs. So I'm actually going to flick all the way through. What I wanted to do was just explain some of the changes that have occurred in 9.3. If you've already been using the replication in 9.2, you'll be aware that because we're using single master, multiple standbys, if the master goes down, we need to do this thing called a failover, where we promote one of the standby nodes to become the new master. Now that failover process in 9.2 and below meant that we had to run something called a shutdown checkpoint at the moment of failover. Now on a very big, very busy database, that could actually take minutes to perform. Now in 9.3, for the first time, what we have introduced is something which we're calling fast failover. Now what happens there is we're actually skipping the checkpoint. So at the moment of failover, that now can happen basically in less than a second. So it will come up almost immediately. And if you do the math on what that means even in a significant cluster, we can switch masters in almost no time at all, and we can actually get better than 5 nines availability now on a Postgres cluster, no matter how many changes are being applied to it. Okay, that's kind of complex in other ways, but previously, because of the time delays, we were only actually able to get 4 nines availability. In terms of complex clusters, we've actually now got what's called timeline following. It's a little bit beyond the novice grade of this lecture to explain what that means, but just to say that large groups of standbys can be managed considerably more easily in 9.3 than we had before. That management is also further improved by the ability to set timeouts on the senders and receivers separately rather than using the same setting overall across all nodes. So actually 9.3 does bring us another iteration closer to really being able to manage our replication configurations fully and accurately and usefully in the real world. But if I'm allowed to just have one more slide, is basically to describe what's going to be happening in the future. We are going to be having further enhancements to physical replication. There's some patches already in the queue that will do that. There's going to be considerably improved controls and, well, basically controls over the way that replication works. One of them is time-delayed replication, but there will be other ones as well. But the next big thing that is coming is what we're calling logical replication. Now, what we mean by that is rather than sending the physical transaction log, we're actually going to process the transaction log into a slightly different form before we send the data across the wire to the replica. Now, logical replication could occur in many different ways, okay? So that processing could occur in lots of different ways. There's going to be one proposed, but actually there could be many different ways of doing that, okay? So the plumbing, which is the way that the masters and the standbys all work together, is one thing, but what's actually flowing down the pipes can and will change over time. And that's going to lead us to a place where we'll be able to do things like online upgrades, and eventually we'll crack this thing called multi-master, which we're also calling bidirectional replication as really a better descriptive phrase for what we're trying to achieve. That is going to take some time, and the most important thing to understand about that is it's not going to be seamless to your application architecture. Some people want it, but they will have to take account of it in their application design. Just to say thank you very much for listening. A lot of the work that we do on replication is developed professionally for our clients, and sometimes when we describe ourselves as a consultancy, nobody really knows what the hell that means. So I've written doing stuff for you, because that's kind of a bit clearer. So anyway, thank you very much. Let's go have lunch.